Oh, welcome again. Today we look at topic 20.1 for IB chemistry. C6H6, benzene, and how it undergoes an electrophilic substitution reaction involving this species, NO2, with a positive here, the nitronium ion. This nitronium ion attacks this electron-rich aromatic ring, and through a series of steps, it takes the place of one of these hydrogens. But before we get into the mechanism of this electrophilic substitution by this positively charged species, I want to question this model. Here we see benzene presented as having 3 double bonds and 3 single bonds. But as you would recall from my earlier video on the properties of benzene, this particular model, first proposed by Kekulé, is now rejected. And we discussed the evidence in this lesson. Let's go in and take a closer look now at the nitration of benzene by this strong electrophile as it searches for the electron-rich center of the aromatic ring. Electrophilic substitution. In looking at the nitration of benzene, it is first necessary to generate the electrophile, the nitronium ion, from a mix of nitric and sulfuric acids. The sulfuric acid protonates or donates a proton to the nitric acid, which leads to the production of this positively charged nitronium ion. This species, with its positive charge, is termed an electrophile, which literally means that it seeks for a center of negative charge. An excellent source of this negativity or negative charge is the aromatic ring of benzene, with the delocalized pi electrons becoming drawn to the positively charged nitronium ion. The nitronium ion goes on to form an association with the ring, receiving 2 electrons and giving 1 electron to the ring. And the ring, in turn, having donated 2 electrons, acquires a positive charge which is delocalized over the entire ring. This positive charge is then lost as an electron from this bond to hydrogen goes into the ring and neutralizes the ring, and a proton is released. The nitration of benzene is now complete. Nitrobenzene, a yellow oil, is the product. Following this nitration of benzene, the presence of sulfuric acid at a temperature of 50 degrees Celsius, the nitrobenzene product then opens the door for a synthetic pathway to produce phenylalanine. To carry out this step, it is necessary to set up a reflux apparatus where the nitrobenzene is heated in a water bath under reflux, which requires constant heating and condensation of a mixture of nitrobenzene with solid zinc and concentrated hydrochloric acid to produce these 7 hydrogen ions. The product is the phenylammonium ion, and zinc is oxidized to zinc 2+ ions, moving from an oxidation number of 0 to an oxidation number of positive 2. The gain in oxidation number suggesting that zinc is oxidized. Oxidation by a loss of electrons. This phenylammonium ion is then deprotonated through the addition of sodium hydroxide, giving the final product, phenylalanine. A simple example of a synthetic pathway where benzene is first nitrated and then it is reduced to phenylalanine.